All right, let's begin. So it's been forever, so let's do a recap. Last time we solved some systems using row reduction. And we discovered certain situations we want to keep an eye on. So last time we solved systems via row reduction. Or you might call it elimination. I want you to notice some terminology that might come up later on. If we do so by reducing to REF and then back substituting to find our answer, we have a name for that. We call that Gaussian elimination, named after, of course, the German mathematician. If you go all the way to reduce or echelon form, then we did, so that's the name of it, that you might see, Gauss-Jordan elimination. We need more power, 2 mathematicians. And we noticed there were 3 scenarios. And that we saw in the 3 different examples for the 3x3 systems that we solved. And those scenarios actually covered all possible cases. There's actually a theorem about this, which I want to actually write down. So, let AX equals B be any linear system of equations. There are 3 possibilities for its solution. You will end up in one of 3 situations. 1, there is no solution. Okay. And we call this inconsistent. So you can say you have an inconsistent system. And we also saw the situation that would bring that on. It's kind of a situation where you have a bunch of zeros, and then it ends with something that's not 0. That does not make any sense, and the system will not have any solution in that case. And this is the only scenario in which you have this situation. If you don't reduce and get a row that looks like that, don't say it has no solution. Otherwise, it will have a solution. But there are 2 kinds of solution that it could have. One is it has a unique solution, meaning only 1. It's just 1 solution, specifically 1. Or 3, the third possibility, it has infinitely many solutions. An infinite amount, right? So you'll either have 0 solutions, 1 solution, or infinitely many solutions. There is no in between. You can't solve a linear system and have 5 solutions. Doesn't make any sense. So both of these situations are called consistent. But they are the only situations that will exist. Notice for the consistent cases, the pattern that you would kind of recognize unique solution. This basically meant that you have the number of pivots you have equals the number of columns in A. That means every variable will have a pivot in its column, which allows you to solve that equation for that variable. And you have infinitely many solutions. Well, that's when the number of pivots is less than the number of columns in A. Of course, you can't have more than. Well, if you include the entire augmented matrix, technically you could have more than, but once you have more pivots than there are in A, you actually end up in the no solutions case. So this means there are some columns where there's no pivot in that column, which means you can't solve for that variable. So that variable can be anything at once, and this leads to what we call a free variable. You could have several. And they're allowed to be whatever they want, and that's why you have infinitely many. Every time you plug in a value for one of these variables, you get a new set of numbers that will work in your equation. And there is no other possibility, right? One of these three things must happen for every linear system. We can, you might have seen this before, but you can visualize it, say, in 2D. If you have two straight lines, their equations would look like the lines of the equations of a linear system, and they can cross and intersect at one point, and that's the unique solution case. They can actually be parallel lines that will never intersect, and that's the no solution case. Or you can have two parallel lines, one kind of right on top of each other, and this is the infinite solutions case. And as you can tell, for straight lines, there is no other possibility. You can't have two straight lines intersecting each other at 2 points. To be able to intersect at 2 points, you'd have to be able to turn back and hit the line again. It's not going to happen. It's a straight line. And of course, in 3D, the same situation. In 3D, now you're visualizing planes, which you don't have to do for this. So you can have like parallel planes, or you can have like one plane doing this, and then two planes doing that. Right? That would be no solution cases, and so on and so forth. Or we can have like the planes intersecting like this, and then you have every one on this line is a solution. We have infinite solutions here, right? Now, so there is a geometric component to this, but we don't need to even go there. Just understand there's going to be three situations for every linear system. So just want to summarize some of the information that we gleaned, hopefully from the last time. Let's move on to the next phase of the class. So as you guys know, I sent that email a couple days ago saying that I had to rethink the syllabus, so from now on we'll be doing quizzes, and I told you guys that today would be our first quiz, so I think we have time. Don't look at me like you're surprised. I even had people responding to me. I have to wake you guys up somehow.
So we don't have quizzes, right? Bro, my stomach went. We need another one. We need another. Do you guys have an extra?
Oh yeah.
Yeah, I was thinking mine or no? sorry.
This is the second time this
Let me
happened.
withdraw.
Because my microphone doesn't do that to me.
One more. Do you need one more?
Yeah.
Bro, I can get that too.
No, I was able to
This is
say,
the second
I
time
saw
this
the email
happened.
that night at 12 something, but I didn't see this email.
Okay, so I want us to work through these problems, but we can't do all of them right away. I'm actually going to teach how to do the very first one. So that is the new thing for today. We're going to learn how to find inverse matrices. Right? About before. So I'm going to talk about inverses. We're going to use it in one way, even though they're useful in many applications. And after that, you'll know everything that you need to be able to do for this. And that's pretty much all the new stuff I'm going to teach you about matrices. I'm not going to really do anything else. But we'll use them later, but all the new material for matrices, this is going to be the end. So let's talk about finding the inverse of a matrix. So recall A n by n must be a square matrix, is invertible, or has an inverse, if there is a matrix which we denote by a to the minus 1. That's just a notation. It does not mean 1 divided by a because there is no division, such that if I take a times its inverse, the result is the n by n identity. And this works out vice versa. A inverse times a is the n by n identity. Now, how do we find one? So your book kind of led into the method by showing you a brute force example. I'm not really going to go through that. I don't really think it's more or less insightful. I can just give you the process. But they just made up a matrix with variables in the components. They multiply them, and then they set up an equation to make sure that certain positions are 1 and certain positions are 0. They set up a whole other system, and then they solve that system. Yeah.
Sorry, is I supposed to say with on the bottom left?
Yeah, such that. Yeah, sometimes I get too lazy here. Okay. But ultimately, they saw a pattern in doing this, which is what I'm going to tell you right now. Step 1. You are going to augment with the identity. So this means you're going to create a matrix that looks like you're going to put your A on one side on the left, and you're going to put the appropriately sized identity matrix on the right. You're then going to start doing row operations. I'm going to count that as step 2. Not just any row operations, you're going to go all the way to the reduced row echelon form. Find the reduced row echelon form. So that's what you're doing here. Now, if your matrix has an inverse, the destiny of this matrix is predictable. You will have the identity appearing on this side, and the matrix that's on this side is going to be the inverse. So 3. If IN appears on the left, A inverse will be on the right. Copy it down. And if IN does not appear, then A has no inverse. Right? We saw that there are some matrices that do not have them. But that's the process. We can find inverses using row reduction.
Is this different from like the transverse?
Yes, it's different. So the inverse is just the guy that has this property. Here's one way to find it. There are other ways to find inverses using like determinants and adjoints and all that stuff, but I don't want to teach any more about matrices. We'll do fine with what we know already. Let's derive something. Now, in terms of how, as far as formulas go, the inverse for a 2 by 2 is something you should have memorized. And let's actually derive it. So, set A equals A, B, C, D. Let's find the inverse. So, as mentioned, I'm going to kind of do this setup over here. I'm going to put A, B, C, D beside the 2 by 2 identity. And I need to find the reduced or echelon form. Now the kids in my other class had some trouble with this. It's easy to kind of see what you want to do with numbers, but once there are letters there, it's there's a psychological barrier. It seems, reminds me of that meme where it was like, and then the devil said to Eve, put the alphabet in mathematics. And everyone just freaks out, that's why it's so hard. But we're just pretending that A, B, C, D are numbers, and we want to find the reduced or echelon form. The same idea is going to hold. My goal is to like kill this C and kill that B. I want to make those guys 0. So let's begin. Here's something I can do. I can say multiply the first row by, say, minus C. And multiply the second row by 8. That creates the same thing in the first column, and then I can just add them and put in the top. Put in the bottom 0. This here will be AD minus BC. Here this will be minus C. This will be A. And here, let me just put this back. AD 1, 0. So it's row 1 plus row 2. So I'm ending up in that situation. Now, I guess I want to kill that B. What I can do here is maybe divide by B. Or if your B is not 0 or whatever. You're going to see that the form is going to work out even if B is 0, but there's going to be a special thing that we need to not be 0 that we'll see. And what I can do here is divide this row by AD minus BC. Now I can subtract. So I have A over B, 0, 1 over B, plus AD minus BC. And I'm subtracting this, so this is minus A over AD minus BC. And here I have 0, 1, minus C over AD minus BC. Here I have A over AD minus BC. this line is great. I want the 0, 1. Here I want 1, 0, so I'm going to multiply by b over a. Multiplying through by b over a. So this is row 1 divided by b, and then I took row, I just left the over. Here was row 2 divided by ab minus bc. What I can do now is multiply row 1 by b over a. I am going to get here 1, 0. Multiply this by b over a. I'm going to get the b's cancel at 1 over a plus b c over a times a b minus b c. We're going to clean this up a little bit. And here I'm going to multiply by b over a. The a is going to cancel, ad minus bc. And the other one is going to be let's clean this guy up a little bit. So if I have 1 over a plus bc over a times ad minus bc, I want to combine the fractions. So what I can do here is common denominator, multiply this by ad minus bc. I would add the fractions now. These guys would cancel. I'll just have ad over a times ad minus bc. A's would cancel. So I'll get d over ad minus bc. So our matrix becomes one, 0, 0, 1. That's the identity on the left side. Over here, I would have d over ad minus bc minus b over ad minus bc minus c over ad minus bc and a over ad minus bc. This means that our A inverse is going to be that guy, which notice that AD minus BC is a common term, at least 1 over that. I can factor that out, put it in front of the matrix AD minus BC, and I've left over D, B minus C, and that's how you find the inverse of a 2 by 2 matrix. I want you to appreciate that we cannot have AD minus BC equaling 0, or else you'll divide by 0, and that will mess things up. If AD minus BC is not 0, though, that formula will actually give you the matrix, and it's something that you should memorize. It's actually a theorem, we just proved it. Let this be a matrix where AD minus BC is not 0, so you have to do that check. Then it is invertible, and the inverse is going to be equal to 1 over AD minus BC times. And you can imagine how you can do this. You swap the guys on the main diagonal, and then you take the negative of everyone else. You can also notice that for the AD minus BC thing, it's kind of multiply along that diagonal, and subtract the product along that diagonal. And we have that. So this is just something we know now. We know how to find the inverse of a 2 by 2. This guy here in the denominator has a name. That's called the determinant of the 2 by 2. Don't worry about what that means. I mean, go into that. That's going to be a whole ordeal. But yeah, so let's actually find an inverse using this formula. Has anyone seen that formula before? Yeah. Well, that's how they got it. It's one way that we're going to get it. Now, I could show you that if we multiply these two, you'll actually get the 2 by 2 identity. But enough variables. Let's actually put in some cold hard numbers. Example. Like AB 1, 2, 3, 4. Does A have an inverse? So find it. Whatever. Now for a 2 by 2, there is a quick check that you can do, and it is in fact this thing over here. You need that to not be 0. Here, AD minus BC would look like 1 times 4 minus 2 times 3. That's going to be 4 minus 6, which is minus 2. This is not 0. So the answer is yes. This has an inverse. And how do we find it? Well, if it's a 2 by 2, I say we're going to use the formula. So we're going to do A inverse equals 1 over AD minus BC. Swap the guys on the main diagonal. Let me just write down. Subtract the guys over here. So for us, that's going to be 1 over negative 2 times, going to swap the 4 and the 1, subtract the 2 and the 3. It's going to be that guy. Yeah, that's the answer. Nothing else to do here.
Do you not multiply it out?
I'm fine with leaving it like that. You could multiply it in, it'll be the same. Now let's see if this works. Let's actually check this. If I were to take A inverse times A, and remember we only have to check one of the two equations. Either check A times A inverse or A inverse times A. What would happen here is that this means I have minus 1/2 times 4 minus 2 minus 3, 1 times 1, 2, 3, 4. And so let's hope we remember how to multiply matrices. Rows times column. 4 times 1 plus minus 2 times 3. Then we're going to have 4 times 2 plus minus 2 times 4. Then we're going to have minus 3 times 1 plus 1 times 3. Then we're going to have minus 3 times 2 plus 1 times 4. It's going to be minus 1/2. In the top, I'm going to have 4 minus 6, 8 minus 8, 3 minus 3 plus 3, minus 6 plus 4. Now if you multiply in, you get 1, 0, 0, 1. So it works. That's the inverse. Here's one use for the inverse. suppose we have a system of equations, and on top of it, we know that A inverse exists. We have a system where the coefficient matrix is a square matrix with an inverse. What can you do about that? Well, here's one thing. You can multiply both sides by the inverse on the left. Matrix multiplication is not commutative, so if I multiply on the left over here, I have to multiply on the left over there. And what's A inverse times A? It's the identity. So this would mean I get IN times X equals A inverse times B. What's the identity times X? Just X. That's what it means to be the identity. Multiplied by anybody, you get itself. And so you can actually find the solution to a system by left multiplication of an inverse. Not right multiplication, it has to be left multiplication. So, here's an example. Let's say I took my same matrix. 1, 2, 3, 4. And set it equal to any random numbers I want, let's say minus 2 and 4. Now I can make up any numbers I want, and I'm going to mention why. Am I going to mention why? I guess I can mention why. Okay. So here I can note that my coefficient matrix is 1, 2, 3, 4. And we know our A inverse is minus 1/2 times 4, 1, minus 2, minus 3. This means to solve this system, our xy is going to simply be A inverse times the matrix minus 2, 4. And that's going to be it matters what side, because this is a 2 by 2, that's a 2 by 1, so the inside numbers match up. This is definitely doable. Row times column, 4 times minus 2 plus minus 2 times 4. And then minus 3 times minus 2 plus 1 times 4. What do we get here? So this is what? Minus 8, minus 8, minus 16. And that's going to be a plus 6 plus 4. It's going to be 10. And so we have 8 comma minus 5 is xy. Now does that actually work? Let's check. Should work if we didn't make any arithmetic errors. If I take 8 plus 2 times a minus 5, what do I get? That's 8 minus 10, which is minus 2. So that one checks out. If I were to take 3 times 8 plus 4 times minus 5, that's 16. Is that minus 20? Or did we make an error somewhere? The 3 is 24 minus 10. Why minus 16? 3 is 24 minus 20. You get 4. We can use inverses to solve systems. There are many other reasons why inverses are important, but that's why we're here.
So wait, now we can avoid doing like the R, yeah?
Yeah, if there's a situation where you would know the inverse beforehand, then you never have to do a row reduction to solve any system with that coefficient matrix. I can just, so if I know a bunch of systems where this side is always the same, and I know the inverse of that, give me the other side, I can just boom, one matrix multiplication and get the answer for all. Boom, boom, boom. Just go around like a stamp. Just kill
Wait, so
them all.
what's an example where this wouldn't work? Where like you couldn't use?
Well, if the inverse doesn't exist,
Oh, it doesn't.
or it's not a square system. So if there's like 3 variables but only 2 rows, it's not square. So it's never going to work. So it has to be a square matrix that has an inverse. Now, I want to do an example like on the handout that I gave you, so you can see how that would work out. When A is larger than a 2 by 2, we don't use formulas, we just compute. So once you get 3 by 3 and higher, things get sufficiently complicated that to memorize a formula is just going to be just as complicated as just doing it. So, because the formulas can get really large. So even in classes where you do a lot of matrix stuff and we really go deep into the matrices, even then no one's going to memorize a formula for the determinant of a 3 by 3 or a 4 by 4. You just know a process and you go through the process. And so let me show you for a 3 by 3. How that's going to actually look. An example here. 2 minus 2 minus 1, 0 minus 2 minus 1, 1 minus 1 minus 1. So we're going to find the inverse of that guy. And this just comes down to going through the process. We're going to find the reducer or echelon form of that. Okay, let's see what you guys remember. What's your first step here? Okay, so what do you want to do?
Move bottom to the top of the row.
Okay, move row 3 up here. It's a nice way to get 1 in the top right corner. That's good. You immediately want zeros below him. You already have a 0. So I'll just copy back row 2. How do I get a 0 here?
Row 3, subtract row 3 times 2 row 1.
Well, 2 times row 3, subtract row 1. Yeah. So 2 row 3 minus row 1. So 2 times this minus that, 0. 2 times this is minus 2. Minus a minus 2, well, that's again 0. 2 times this is minus 2. Minus a minus 1, that is minus 1. 2 times this is 0, minus that, minus 1. 2 times 0, minus that, you get 0. 2 times this is 2, minus 0, so we get that. So that's nice. So remember, in your first step, you want the top leftmost pivot and zeros below. Now, once you achieve that, our next goal is to kind of have a pivot here and get zeros below that. Now Now at this point we can turn this into a 1 by just dividing through by -2. But I'll actually hold off on that a little bit because I don't want to create fractions here and then have to be moving fractions around. So eventually I'm going to divide this guy by -2 to get the pivot there. But for now it's safe, but we're coming back to that. We're coming back to here. Okay. So let's actually move on to this guy and worry about getting the zeros above. So first thing, we can clean up that guy a little bit. Just multiply by -1. So now it's like that. But then what I can do is say, take this minus that. Yes?
For the second step there, did you just turn the first row into row 3? Or did you swap row 3 and row 1?
For here?
For the next one.
Yeah, I literally just, I moved this here, so that's row 3, came up top. I copied down this row, I didn't do anything to it. And then here I did a calculation using the old row 1 and row 2.
The old row?
Yeah, so I took 2 row 3, 2 times this, and then I subtracted that.
Okay.
Because that gets this to be a 2 and subtract that 2 and get this here. So I did a type 3 at the bottom. And here, what I can do is row 2 minus row 3, 0 minus 0, minus 2 minus 0, minus 1 minus a minus 1, 0 minus a minus 1, 1 minus a 0, and I can do a 0 minus a 2. And for the top one, I can take row 1 minus row 3. So 1 minus 0, minus 1 minus 0, minus 1 minus a minus 1, 0 minus a minus 1, 0 minus a 0, 1 minus a 2. Now what I can do is do something like, I'm going to take an extra step here. Probably, but let's say, I mean, at this point I think it's okay to use the fractions a little bit. It's not going to kill us. Save us a step. So I just copied row 3. I'm going to divide this through by -2. And then I'm going to subtract these two, or add these two. So take row 1 plus the row 2 over -2. And I'm going to get this plus that, 1, this plus that, 0, this plus that, 0, this plus that, 1 plus a minus a half, gives me positive 1/2, this plus that, minus a half, this plus that, 0. Notice that the identity is on the left, so this is my inverse. You can factor out a half. That's my guy. Let's check to make sure we didn't make a mistake. Hopefully we didn't make a mistake. So if I take this one, times the original, what are we going to have? Okay. 1 times 2 plus minus 1 times 0 plus 0 times 1. Then we're going to have 1 times minus 2 plus minus 1 times minus 2 plus 0 times minus 1. Then we're going to have 1 times minus 1 plus minus 1 times minus 1 plus 0 times minus 1. Next row, minus 1 times 2 plus minus 1 times 0 plus 2 times 1 minus 1 times minus 2 plus minus 1 times minus 2 plus 2 times minus 1 minus 1 times minus 1 plus minus 1 times minus 1 plus 2 times minus 1 2 times 2 plus 0 times 0 plus minus 4 times 1 2 times minus 2 plus 0 times minus 2 plus minus 4 times minus 1 2 times minus 1 plus minus 1 times minus 1 plus 2 times minus 1. So we're going to get 1/2 times 2 plus 0 plus 0 minus 2 minus 2 minus 2 plus 2 because it's a negative 1, so that's 0 minus 1 minus 1 minus 1 plus 1 plus 0 here minus 2 plus 2 plus 2 plus 2 that's plus 4 minus 2 plus 1 minus 2 4 minus 4 minus 4 plus 4 and minus 2 plus 1 this gives me minus 1 where am I? Okay. This should be a 4, right? So what does that go up to? Does that give us a 2? Where? Oh, negative 4. Does that give us a 2? No.
That's 3.
This is, we messed up a lot on this one. Okay, so that's minus 2. I'm doing 2, 0, minus 4. 2, 0, minus 4. So that's minus 2 plus 4. Okay. So that actually works, right, when I divide 2 by 2. So that's the inverse. So go forth and do that handout. We'll actually do it tomorrow, but it's very important that you try it on your own to see where you're getting stuck.